metal casting. In this metal casting, we have seen in the previous class that metal casting is the oldest manufacturing process and it has started as an art. Today it has emerged as a technology. We have seen introduction for the metal casting in the previous lecture, and we have seen that the metal casting lies in the principle of making a cavity of the shape of the component which we are going to manufacture. If we are going to manufacture a particular shape, that kind of cavity we have to create in a sand mold. Then in that cavity we will be pouring the molten metal. For that we will be using a pattern which will be acting as the model. The pattern is the replica of the component which we are going to manufacture. So this we will call it as the pattern. Most of the times the pattern is made up of wood, sometimes it is made up of metal, sometimes it is made up of wax, sometimes it is made up of plaster of Paris. So we have seen the advantages and the limitations of different pattern materials in the previous class. We have also seen that the pattern will be the replica of the component which we are going to manufacture. However, the geometry of the pattern is not exactly same as that of the component which we are going to manufacture. The geometry of the pattern will be slightly different from the component which we require. This difference comes because of certain allowances. We need to give certain allowances to the pattern, and these allowances we have briefly discussed in the previous class. These are the pattern allowances. One is shrinkage allowance or contraction allowance, and another one is draft or taper allowance, machining or finishing allowance. Next one, distortion or camber allowance. Next one, the wrapping allowance. The shrinkage allowance, why it is given? The shrinkage allowance is given because the metal in the liquid state, when it is solidifying, it undergoes shrinkage. If we want a particular size casting, yes, we make the pattern. If the geometry of the pattern is exactly same as that of the component, we make the similar cavity. The geometry of the cavity will be similar to that of the pattern. The cavity geometry will be identical to the component's geometry. We pour the molten metal and it will be solidifying. During solidification, it undergoes contraction. Finally, we will be getting a smaller casting. So to counteract this effect, we have to make the pattern a little bigger than the casting size. Means we will be giving shrinkage or contraction allowance, and this shrinkage allowance is given as per this table. For different metals, this shrinkage allowance has to be given like this. When we are making a grey cast iron casting up to 2 feet, the shrinkage allowance should be 0.125 inch per feet. From 2 feet to 4 feet, the shrinkage allowance should be 0.105 inches per feet. Over 4 feet, the shrinkage allowance should be 0.083 inches per feet. When we are casting, making a casting of cast steel up to 2 feet, the shrinkage allowance should be 0.251 inches per feet, and from 2 feet to 6 feet, the shrinkage allowance should be 0.191 inches per feet, and over 6 feet, the shrinkage allowance should be 0.155 inches per feet. When we are making a casting with aluminum up to 4 feet, the shrinkage allowance should be 0.155 inches per feet. From 4 feet to 6 feet, the shrinkage allowance should be 0.143 inches per feet. Over 6 feet, the shrinkage allowance should be 0.125 inches per feet. When we are making a casting of magnesium up to 4 feet, the shrinkage allowance should be 0.173 inches per feet. Over 4 feet, the shrinkage allowance should be 0.155 inches per feet. Let us see a problem how to incorporate these allowances when we are designing a pattern. When we are making a casting made up of cast iron of the following dimensions. So, let us assume that only shrinkage allowance need to be given. Let us ignore the other allowances. Then if this is the geometry of the casting, what should be the dimensions of the pattern? So, let us examine the geometry of the casting. Here we can see one side 14 inches, all dimensions are in inches, and another side 18 inches, and this height is 8 inches, there is a hole and it is diameter is 6 inches. Let us see how to calculate the shrinkage allowance and what should be the final dimensions of the pattern. The shrinkage allowance for cast iron up to 2 feet is 0.125 inch per feet. So, for dimension of the 18 inch side, allowance is 18 into 0.125 divided by 12, that comes to be 0.1875 inches. We can round it to 0.2 inches. And there is another side whose length is 14 inches, and for its allowance it is given by this 14 into 0.125 by 12, that comes to be 0.146 inches. We can round it to 0.15 inch. And there is another dimension 8 inches. Its allowance can be calculated like this, that comes to be 0.8 into 0.125, sorry 8 into 0.125 whole divided by 12, that comes to be 0.0833 inches. We can round it to 0.09 inches. And there is the dimension of 6 inches, that is the hole, and its allowance will be like this, 6 into 0.125 divided by 12, that comes to be 0.0625 inches. We can round it to 0.07 inches. So, the pattern dimensions will be as follows. The first dimension will be 14.15 inches. The another side where the actual dimension of the casting is 18 inches, now here we have to give 18.2 inches, and the diameter of the hole is 6 inches, now we have to give 5.93. The height of the casting is 8 inches, now we have to give 8.09 inches. So, this will be the final dimensions of the pattern considering only the shrinkage allowance. Now, next one is the draft allowance or the taper allowance. What is this draft allowance? Yes, when we mold the pattern in the mold box, we ram the molding sand, and after compacting the molding sand, we have to withdraw the pattern. When we are withdrawing the pattern, there is a very chance the vertical surfaces of the pattern may be sticking to the molding sand, and it is difficult to withdraw the pattern. For that purpose, we give a taper to the vertical surfaces. So, this is known as draft allowance or taper allowance. Let us see what happens when draft allowance is not given, or what happens when draft allowance is given. Let us see this molding system, where in one case we are molding without taper. This is the pattern, this is the molding box, and this is the molding sand, and here we have molded without any taper. And when we are after compaction of the sand, when we are withdrawing the pattern, there is every chance it will be breaking the sand, the mold may be damaged. So, this is not desirable. On the other case, here we can see the pattern where we have given the draft, the vertical surface is tapered. Now, after compaction of the sand is over, when we try to withdraw the pattern, this will become easy to withdraw the pattern. So, this is easier. In this case, the mold will not be breaking, the mold will not be damaged. So, this is safe, this is desirable. So, in this case we have given tap relevance, this is desirable, and these are the draft allowances to be given for various metals. So, this is the pattern material and height of the given surface, and if it is 1 inch, the draft angle should be 3 degrees. This is if it is external. If it is internal, it should be 3 degrees. And when the height is 1 to 2 inches, the draft angle should be 1.5 degrees for external. For internal, it should be 2.5 degrees. And from 2 to 4 inches, the draft angle should be 1 degree, that is for external. For internal, it should be 1.5 degrees. And when the height is 4 to 8 inches, the draft angle should be 0.75 degrees for external, and for internal it should be 1 degree. And from 8 to 32 inches, the draft angle should be 0.5 degrees for external, and if it is internal it should be 1 degree. And when the pattern material is made up of metal or plastic, the draft allowance should be like this. For 1 inch height, it should be 1.5 degrees if it is external. For internal, it should be 3 degrees. And from 1 to 2 inches, the draft angle should be 1 degree for external, and for internal it should be 2 degrees. From 4 to 8 inches, the draft angle should be 0.5 degrees for external, and it should be 1 degree for internal. From 8 to 32 inches, the draft angle should be 0.5 degrees for external surface, and it should be 0.75 degrees for internal surface. Machining or finishing allowance. What is this machining allowance? We know that the pattern material is made up of wood in most of the cases. If it is the sand material is rough, and when we compact the pattern in the sand, the mould cavity, the external surface of the mould cavity will have a rough surface. And when we pour the molten metal will be occupying in the cavity, and after solidification, the external surface of the casting will have a rough surface. This rough surface is not acceptable for any application. So, to get a fine surface finish, we have to machine it. When we machine it, its size becomes smaller. So, if we do not consider this effect, and if we make the pattern size exactly same as that of the casting, fine, the cavity will be same size as that of the casting component, and during solidification it will have a rough surface after solidification, and after machining its size becomes small. Now we have to counteract this effect. For that purpose, considering this effect, considering this machining, we have to make the pattern size little bigger than the required size of the casting. So, this is known as machining or finishing allowance. And the machining allowance of various metals are like this. For cast iron, up to 12 inches, the machining allowance should be 0.12 inch. From 12 to 20 inches, the machining allowance should be 0.2 inches. From 20 to 40 inches, the machining allowance should be 0.25 inches. For cast steel up to 6 inches, the machining allowance should be 0.12 inches. 6 to 20 inches, the machining allowance should be 0.25 inches. 20 to 40 inches, the machining allowance should be 0.3 inches. And for non-ferrous metals, up to 8 inches, the machining allowance should be 0.09 inches. 8 to 12 inches, the machining allowance should be 0.12 inches. 12 to 40 inches, the machining allowance should be 0.16 inches. Now let us solve one more problem. So here is a this is the geometry of the casting which we want. The casting shown is to be made by cast iron using wooden pattern. Assuming only machining allowance, calculate the dimensions of the pattern. So, here we can see one side is 14.15 inches, another side is 18.2 inches, and there is a circle that is 5.93 and the height is 8.09. And how to take this machining allowance, how to calculate this machining allowance. So, the machining allowance for cast iron for up to 12 inches is 0.12 inches, from 12 inches to 20 inches it is 0.2 inches. So, for dimension of 18 inch the allowance is 0.2 inches. For dimension of 14 inch side the allowance is 0.2 inches. For dimension of 8 inches the allowance is 0.12 inches. For the dimension of 6 inch the allowance is 0.12 inches. The pattern with the after giving the machining allowance will be looking like this. The 14 point that side will have the dimension 14.2 and this side 18.2 and this side 5.88, here it is 8.12. So, this is the final geometry of the pattern after considering the machining allowance also. Next one, distortion or camber allowance. What is this distortion allowance? Distortion means damaged. The shape will be spoiled, the shape will be disfigured in a disorderly way. What are the reasons for distortion? One is internal stress and another one is non-uniform cooling of casting. When the casting contains different sections where the sections are of different thicknesses, one section will be solidifying fast, another section will be solidifying later, and there is a difference in solidification. This leads to residual stresses and this leads to non-uniform cooling of the casting. So, here we can see the example of a distorted casting. So, this is the required casting, this I section, and because of this distortion finally the casting is appearing like this. This is the actual requirement of the casting, but after solidification the casting is looking like this. So, this is the effect of distortion, and when we are designing the pattern we have to take this effect into consideration. We have to design the pattern such a way that this distortion will be overcome. How to counteract this distortion? Measures to be taken to prevent distortion. First one is we will provide machining allowance so that even if the casting undergoes distortion, wherever it has gone distortion we will machine it. We will machine until it becomes the required shape, until it gets the required shape. Another one is we provide suitable allowance, that is the inverse reflection. What is this inverse reflection? I will show you. So, this is the required casting geometry, this is the required casting shape, and if we do not give any camber allowance, this will be the final shape of the casting, this will be the final shape of the casting. Now, we have already anticipated this camber allowance, so we have designed the pattern like this, and we have designed the pattern like this, and with these patterns when we make the mold, when we pour the molten metal after solidification, yes, it will be that the distortion effect continues to rule, but in its attempt for distortion it will bring to the normal shape. So, this is how we can counteract the distortion effect. So, this is the camber allowance, we are anticipating the distortion and we are making the geometry of the pattern in the other direction. So, this is the camber allowance. Next one, wrapping allowance. What is this wrapping? We have already seen that we use the pattern which is the replica of the casting which we are going to manufacture. This pattern we will place inside the molding box, we will ram the molding sand, we will compact the molding sand. After compaction is over, we have to withdraw the pattern. For withdrawing the pattern, we have to wrap the pattern. Wrapping means shaking gently. Left side and right side will be shaking. What happens when we wrap the pattern or when we shake the pattern? What is the effect of wrapping on the mold cavity? The mold cavity will become little bigger. So if we want the casting of a particular size, and if we do not consider this wrapping effect, and if we make the pattern size exactly same as that of the casting, what happens after withdrawal of the pattern? The cavity is slightly bigger. When we pour the molten metal, yes, we have already given shrinkage allowance, we have already given machining allowance, and because of this wrapping, the cavity has slightly become bigger, and the casting is taken out, its size is much bigger, and to bring it to the required size, we have to do more machining. For that we have to put more efforts, this costs more. So that is the effect of this wrapping. So we have to design the pattern in such a way that this wrapping effect will be minimized. What we have to do to minimize this effect? We have to give the negative allowance. Means if we want a particular size casting, not that we will make the casting, not that we make the pattern exactly of the same size as that of the casting, but we will make the size of the pattern little smaller than the actual size of the casting. When we make the pattern size little smaller than the casting size, when we do this wrapping, then it becomes little bigger, then that effect will be nullified. So this wrapping allowance is the negative allowance, and how much it should be, and it is done in the shop floor, and the people who are working in the molding shop, by experience they used to do this, and they used to take care of this wrapping effect. And now let us see the types of patterns. There are several types of patterns, and we will see some important types of patterns. One is single piece pattern, another one is split or two piece pattern, third one match plate pattern, fourth one gated pattern, fifth one sweep pattern, sixth one loose piece pattern, seventh one skeleton pattern, eighth one cope and drag pattern. Let us study these in detail. Single piece pattern. So suppose this is the geometry or shape of the casting to be obtained. So the pattern will be like this. And what is the shape of the casting? Shape of the casting is very simple. So here we make only one piece. So this will be molded in the drag box. Drag box means the lower molding flask. In the lower molding flask we will compact this pattern, and we will get the required shape, required cavity, and we pour the molten metal. So this single piece pattern used where the job is very simple. Next one, split or two piece pattern. This split or two piece pattern is used when we are making castings of intricate shape. So the pattern is split along the parting surface, means in the middle it will be split into two halves. One half of the pattern will be molded in the drag box, and the other half of the pattern will be molded in the cope box. Then these two molding boxes will be clamped carefully so that they will be properly aligned. Then of course we will make the provision for sprue, runner and gating system, and then we pour the molten metal. And I will show you an example. So, this is the split phase pattern. For example, this is the pattern required when we need to manufacture a dumbbell. So, this is the pattern. So, the pattern is split into two pieces, upper piece, upper half and lower half, and there will be one dowel pin will be there for the upper half, and there will be hole for the bottom one, lower one. The pin will be, has to rest in the hole, then they will be properly aligned. So, this split pattern is used when intricate shapes are to be manufactured. So, this is the dumbbell. This dumbbell is manufactured by casting, and for this purpose a split pattern has been used. Next one, match plate pattern, and this match plate pattern, it consists of a match plate, and like a split pattern, one half of the pattern will be clamped on upper side and other half of the pattern will be clamped on the bottom side. Not only one pattern, we can use more patterns and we can clamp them, one half on the upper side and other half on the bottom side we can clamp, and all of the upper halves and the lower halves will be clamped to a plate which we call it as match plate. So, this is the match plate, this one is the match plate, and this is one pattern, this is one pattern and this is one pattern. So, here we can see the patterns are already split, the one half is clamped on the upper side and other half is clamped on the lower side. Here also one half is clamped on the upper side and the other half is clamped at the lower side, here also. Now, what happens? Initially we take the drag box and we place the molding sand, and then we place this match plate and it will be compacted. Then over this we place the cope, again we place the sand and that sand will be compacted, and while doing so we have to take care that the drag box and cope box are properly aligned, otherwise after the withdrawal of the pattern there will be misalignment. So, for that there will be dovetail pins will be there, so that they will be properly aligned, and material of this pattern, match plate pattern, is metal. Wood is not possible. A match plate pattern is always made up of metal, and examples are piston rings of IC engines, they are made by match plate pattern. Next one, gated pattern. Here we can see so many patterns. Here is one pattern, here is one pattern, 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 one pattern. All these patterns are connected. So, this is the runner, so this is the gate, this is the gate, this is the gate. So, they are all connected and there is one common sprue, here is one sprue through which we pour the molten metal. So, this is used for small castings. So, for small casting, whenever we want to make a small casting, for each casting if we have to make a mold, that mold itself takes lot of time, and at a time if we have to make some 20 small castings, 20 molds if we have to prepare, it takes lot of time. Instead, all these 20 patterns will be placed, they will be joined like this, and we will design a gated pattern, and all this, the entire system can be molded at a time, so that the molding time will be minimized. And there is another advantage of this gated pattern. Whenever we are making a mold, along with the mold we have to make a provision for sprue, for riser and for the gating system. Suppose if we are making a casting of 1 kg, the cavity, the molten metal which is flowing into the cavity will be about 1 kg, and the molten metal which will be occupying in the sprue, which will be occupying in the runner, which will be occupying in the gating system, that will be about 0.25 kgs. So, if we have to make a 1 kg casting, we have to pour molten metal about 1.25 kgs. So, that is the casting yield. Casting yield is the ratio of the weight of the casting divided by the weight of the poured metal into 100. So, in general the casting yield comes to be between 70% to 80%, and for each casting, if we have to design the gating system, designing that gating system takes time, and when we pour the molten metal is occupied in the sprue and runner and the gating system. In each case there is a wastage of the metal, there is a loss of casting yield. On the other hand, when we join these patterns like this, when we make a gated pattern, when there is a common sprue, when there is a common runner, the molten metal which is wasted for the runner and for the gates is less. The molten metal which is wasted for riser is less. This in turn increases the casting yield. This in turn reduces the cost of the process. So, this is used for small casting. This cannot be used for bigger castings. Next one, sweep pattern. This is very important pattern, very interesting pattern too. And what is the principle lying behind this sweep pattern? This is a 2-dimensional pattern. All the patterns are of 3 dimensions, but this is a 2-dimensional pattern. Here we can see, say this is the shape of the casting, a 3-dimensional shape which is symmetrical. So, instead of using a solid pattern, what we can do is we can use a plate. The plate, this hatched one is the plate, just 2-dimensional plate like this. This one is the plate. So, this plate is clamped to a post, central post, and it is kept inside the molding box, and this is the green sand. Green sand means molding sand with moisture, and we insert this sweep, we call this board as sweep. So, we slowly start rotating about this post, we rotate. As it is rotating, it removes the material, slowly we will increase the depth and it removes the material, Finally, the entire sweep is inserted into the molding sand. Finally, the required cavity which is identical to the shape of the component which we require is created. Then we withdraw this sweep, that is the sweep pattern we withdraw. We even withdraw this post. Whatever is done so far is done in the drag box. Now we will place the cope box over this. Then we make a provision for sprue, we make a provision for gating system, we will make a provision for riser. Then we pour the molten metal, the required casting is obtained. But what happened here? The pattern which we have used is not a 3-dimensional, it is a 2-dimensional pattern. So, this has got certain advantages, lie in the sense we do not have to spend so much time for making the pattern, especially say when the casting has got some complex surface, say symmetric and complex surface, that time making the pattern requires lot of time, it requires lot of efforts. But here we are not making a 3-dimensional solid pattern, we are making only a 2-dimensional sweep pattern. It is just a board, just a sweep. By rotating this, we are getting the required shape. So, we are not spending so much time for making the pattern. We are not spending so much of time for making the mold. We are not spending so much money for making the pattern. So, this is the advantage of the sweep pattern, but it has got certain limitations. This can be used only for circular jobs or symmetrical jobs, where the jobs have some circular cross section or some symmetrical cross section. In such cases only we can use. otherwise it is not possible to incorporate this sweep pattern. Next one, loose piece pattern. Now let us consider a casting of this shape. It has got a section like this, and here there is a projection and here there is a projection. Now what kind of pattern can be used? Certainly it can't be a single piece pattern, and to making it split pattern is also difficult. Then how to make the mold for making this casting? So here what we do is, here there are two projections A and B. What we do is, this A is separated, this B is also separated. Whenever required, they can be placed nearer to the main pattern. This also can be placed nearer to the main pattern. This whole system, the big pattern and these two loose pieces will be molded in the drag box, and this will be molded upside down, means the projections A and B will be coming upwards in the drag box. And after compacting of the sand is over, after molding is over, then we have to withdraw. Initially we withdraw this A, it is so easy, there is a taper, so very easily we can withdraw this A. Similarly B also very easily we can withdraw from the drag box. We will be withdrawing from top, this will be molded upside down, then we will withdraw this pattern. So this loose piece pattern has got certain advantages, where some loose pieces have to be molded, where some loose details are to be molded, that time we use loose piece pattern. Next one is skeleton pattern. This skeleton pattern is used for making very huge castings. Suppose big turbine impellers are to be manufactured. These turbine impellers are very big. In such times we have to use skeleton pattern, means when the pattern requires lot of pattern material, instead of using the solid pattern we can use hollow pattern. So that is the skeleton pattern. What we require, we have to make the outer surface of the mold cavity. For making the outer surface of the mold cavity, whether we use solid pattern or hollow pattern, it does not matter. So we use skeleton pattern, which is the hollow pattern, in which we save the pattern material. So this is used only for huge castings, this cannot be used for small castings and medium size castings. Next one, cope and drag patterns. So this is again used for making big castings. It is similar to split pattern, but in the case of the split pattern, the cope off and the drag off of the patterns are compacted in the cope box and drag box respectively, and the gating system, that is the runner and the ingates, they are designed, they are molded in the drag box. But here even the runner and the ingates, they will be rammed, they will be molded equally in the cope and drag. So this is the unique distinction of the cope and drag patterns, where the size of the molding box is very big, where it can't be done by one person. So it is done at different places. So half of the pattern will be done, will be molded at one place, even half of the gating system, and the other half of the pattern and the other half of the gating system will be molded at another place by another person. So this is used for big castings. Now let us come to this core and core prints. Need for cores. Why we have to use the cores? To create holes and to cavities inside a casting. Whenever we have to make a casting with some holes or some cavities, it is that time we have to use cores. And there is, we can see another term, core print. Yes, when we make a core, there should be some place in the mold so that the core will be resting. That place has to be created. To create that place where the core will be resting, we use core prints. So, core prints are the additional projections on the pattern. On the sides of the pattern, there will be some projections. When we put the pattern inside the molding box, and when we put the molding sand and when we compact it, the projections outside the projections also, the mold is sand ramped. And when we withdraw the pattern, even the projections will create some hole, some space. In that space, the cores will be resting. Let us see, this is the component to be manufactured and this is the pattern. So, the pattern will have this shape and this is the core print. Actually, to make this kind of shape, this portion is not required, this projection is not required even, right. But why we have kept this projection? With this projection, we are creating a place where the core will be resting. So, this is the core made up of sand. After cavity is created, we are inserting this core into the mold cavity, and to place this core, there is a place here where we are supporting the core here and here. And how that place is created? That seat, how that seat is created? Because of these projections. If these projections are not there, this place would not have been there, this place would not have been there, then it is impossible to support the core. So, by using core prints, which are the extra projections, we create the seat where the core can rest. So, that is the purpose of core and core prints. Now, let us see properties of molding materials. We have seen the different allowances, different pattern allowances, different types of patterns also we have seen. Now, let us see the properties of molding materials. Molding material means the molding sand, and we add clay and moisture. And what kind of properties it should possess? There are certain properties which the molding sand is expected to possess. One is flowability. Flowability, what does it mean? It is the ability of the molding sand to flow and get all the details of the pattern exactly occupied and get all the details of the pattern, and so that when we pour the molten metal into the cavity, it gives the exact dimensions, exact details. There may be some sands which even if you compact, it will not take all the details, only it will be sticking outside, but it will not be sticking to the interior details. At such times, it is difficult to get the shape of the casting, but a good molding sand should have the flowability. It is the ability of the molding sand to flow and get compacted all around the pattern and to take up the required shape. Next one is refractoriness. What is this refractoriness? It is the ability of the molding sand to withstand high temperature. Yes, when we make the mold, after making the mold, after withdrawing the pattern, we pour the molten metal. The molten metals are at very high temperature. If we are making an aluminum casting, it is heated about 700 degrees centigrade. If we are making a casting of cast iron, it is heated about 1400 degrees centigrade. At such high temperatures, there is every chance the sand may fail, the molding sand may fail. It may no longer retain the shape, but a good molding sand should retain the shape and retain its strength, and it should resist the high temperature. That is the refractoriness. It is the ability of the molding material to withstand the high temperature of the liquid metal to be poured. The refractoriness of the silica sand is highest. Next one, permeability. This is another important property. When we pour the molten metal into the mold, it is going and keeping in touch with the molding sand. The molding sand contains moisture. When the molding sand goes in contact with the molding sand, the moisture turns into vapor and some other hot gases are produced. This vapor and hot gases have to be sent out. They should escape out of the mold. If they stay inside the mold cavity, they will result in blowholes or pin porosity or other defects. And a good molding sand should have the good permeability. It means though it is compacted tightly, still when the molten metal is poured, it should allow the hot gases to pass through it. You should allow all the hot gases to pass through it, even in the compacted stage, even in the compacted condition. That is the permeability. It is the ability of the molding material to allow hot gases to pass through it. Next, green strength. This green strength means, green means the presence of moisture. Yes, a good molding sand should have green strength, means it should have strength when the moisture is present. The molding sand that contains moisture is termed as green sand. Green strength is the ability of the green sand to retain the shape of the constructed mold. Because moisture is present, it should not lose its strength. So, a good molding sand should have good green strength. Let us see the dry strength. Dry strength means in the absence of moisture. Yes, immediately when we pour the molten metal, the moisture will be evaporating. It is possible some sands may have good green strength, but the moment the moisture is evaporated, they may lose the strength. But a good molding sand should have good dry strength, means even in the absence of the moisture, even when the moisture is evaporated due to the pouring of the molten metal, it should have good strength. It should retain the shape of the cavity. It should retain the force created due to the pouring of the molten metal. That is the strength. That is the dry strength. Next one, hot strength. It is the ability of the molding material to retain the exact shape of the mold cavity at an elevated temperature. Dry strength is the strength just in the absence of moisture, whereas hot strength is that strength where it possesses the strength when the mold is heated to an elevated temperature. Now, initially the mold is in green state, there is moisture in it. Yes, it has strength. Then we pour the molten metal, the moisture is evaporated. So, it has got dry strength, but that is not enough. It should possess hot strength, means after drying off the moisture, as we keep pouring the molten metal, the mold is heated to a much higher temperature, because the molten metal's temperature is about 1500 degrees centigrade. If we are making a cast iron casting, the mold is heated to a much high temperature. At much high temperature, the mold should not lose its strength, it should retain the shape. So, that is the hot strength. It is the ability of the molding material to retain the exact shape of the mold cavity at an elevated temperature. Next, adhesiveness. It is the ability of the molding sand to stick with the walls of the molding boxes. Yes, it is important that the molding sand should be sticking to the molding boxes. Otherwise, when the mold is ready, we will be carrying the molding boxes. It is possible that the mold may slip out of the molding box and it may fall down, but that should not happen. After compaction is over, the molding sand should be sticking to the walls of the molding box. That is the property of the adhesiveness. A good molding sand should have good adhesiveness. It means it should be sticking to the walls of the molding box. Next one, collapsibility. It is the ability of the molding sand to get collapsed after the casting solidifies. Yes, we pour the molten metal and after some time the molten metal solidifies. After solidification is over, we have to take the casting out. Then we start breaking the molding sand. At that time, it should allow us so that we can break the molding sand easily. And if it is resisting us, to break the molding sand, then we have to put more efforts. Then if we have to put more efforts, we have to use more labor, we have to spend more money, that increases the cost of the process. Yes, a good molding sand should be easily collapsible after solidification is over, that is the collapsibility. Next one, the durability. So, when we pour the molten metal after solidification, we break the molding sand and we take the casting outside. Then this sand which we have broken, we cannot discard, again we have to reuse it. This sand again and again we will be using for making several molds and making for several castings. So, a good molding sand should be in a position so that we can use it again and again. So, that is the durability. So, it is the ability of the molding sand to withstand repeated cycles of heating and cooling during casting operations. Yes, during casting operations it is subjected to heating and cooling. So, a good molding sand should be able to withstand these repeated cycles of heating and cooling. So, in this episode we have seen different pattern allowances, shrinkage allowance, the machining allowance, draft allowance and camber allowance. We have also seen different types of patterns: single piece pattern, split piece pattern, match plate pattern, gated pattern, skeleton pattern, cope and drag pattern. We have also seen the different properties of the molding sand. What are the ideal properties which a good molding sand should possess, we have seen. And in the next episode we will be seeing the mold sand composition, that we will be seeing in the next episode. Thank you.